Welcome again to Quantum. In this talk, we examine how electric and magnetic fields shape quantum mechanics, leading to the integer quantum Hall effect. We explore Landau levels, von Klitzing's Nobel-winning experiment, and quantized resistivity plateaus driven by topology and magnetic field effects. While we won't delve into them here, this phenomenon also connects to topological quantum mechanics and the emergence of geometry from quantum dynamics. Let's dive in. Impact of an electric field. Previously, we explored the quantum behavior of a charged particle in a uniform magnetic field, which led to the well-known Landau energy levels. Now, we introduce a perpendicular electric field and describe the system within the Landau gauge framework. The presence of the electric field adds an additional potential term to both the Lagrangian and Hamiltonian. Despite this modification, the wave function retains its exponential dependence in the y direction, reflecting the translational symmetry along this axis in the Landau gauge. This choice of ansatz leads to a modified Hamiltonian that explicitly incorporates momentum dependence. The resulting energy spectrum reveals a shift in the Landau levels due to the electric field, breaking the degeneracy in momentum space. The corresponding wave functions take the form of quantum harmonic oscillator states, displaced from the origin by an amount proportional to the electric field. Since the energy now depends on momentum, the system exhibits a drift motion, with a velocity in the y direction given by the negative ratio of the electric field to the magnetic field, representing the quantum analog of the classical E cross B drift. Experimental discovery of the integer quantum Hall effect. The integer quantum Hall effect stands as one of the most striking discoveries in condensed matter physics. First observed by Klaus von Klitzing in 1980, this phenomenon revolutionized our understanding of electron transport in two-dimensional systems and led to his 1985 Nobel Prize in Physics. The integer quantum Hall effect is characterized by the quantization of the Hall resistivity. When a two-dimensional electron gas is subjected to a strong magnetic field at low temperatures, the Hall resistivity does not change smoothly. Instead, it forms distinct, well-defined plateaus at specific values. The longitudinal resistivity vanishes on these plateaus, while the magnetic field at the center of each plateau is the value of the magnetic field at which the first new Landau levels are filled. Each plateau corresponds therefore to an integer filling factor, where the resistivity is quantized in units of the von Klitzing constant. This constant represents the fundamental quantum of resistivity and is defined in terms of Planck's constant and the electron charge. A remarkable feature of this effect is that these plateaus remain unchanged despite variations in experimental conditions such as temperature, impurities, or small fluctuations in the magnetic field. The reason? This quantization is a direct consequence of the fundamental topological properties of the system. As the magnetic field is tuned, the resistivity undergoes abrupt jumps between plateaus. At these transition points, the longitudinal resistivity exhibits sharp spikes, indicating a fundamental change in the electronic transport behavior. Theoretical derivation of the quantization of the Hall resistivity. To understand the integer quantum Hall effect, we turn to the quantum mechanics of a charged particle moving under the influence of a perpendicular strong magnetic field. Indeed, in a strong magnetic field, electrons move in circular orbits, forming discrete energy levels known as Landau levels. The energy of these levels increases linearly with the quantum number, and each level exhibits a macroscopic degeneracy, which depends on the magnetic flux per unit area. In classical Hall physics, the Hall resistivity follows a simple relation proportional to the inverse of electron density. However, in the quantum regime, experimental observations reveal a discrete stepwise pattern, instead of a continuous change where discrete jumps in the Hall resistivity occur in a sequential, ordered manner, forming a staircase-like structure. This is where quantum mechanics diverges from classical predictions. The quantum Hall effect is confirmed when we analyze electron density. When a given number of Landau levels are completely filled, the system reaches a stable quantum state, leading to the observed plateaus. A fully quantum mechanical approach defines the current density in terms of the wave functions of the occupied Landau levels. It is found that the current remains strictly perpendicular to the applied electric field, ensuring that power dissipation is exactly zero. This current is also found to be proportional to the filling factor nu and inversely proportional to the quantum of flux. This leads, by using Ohm's law, to the characteristic behavior where the system is a perfect conductor in the transverse direction while behaving as an insulator along the longitudinal direction. The condition of zero longitudinal conductivity is central to the robustness of the quantum Hall effect. It guarantees that all current flows exclusively along the edges of the sample, forming what are known as edge states, which are responsible for the highly stable quantization of the Hall resistivity. The role of the magnetic field. The magnetic field strength plays a crucial role in determining the position of each plateau. The center of each plateau is defined by a specific value of the magnetic field, which ensures that an integer number of Landau levels are completely filled. This value depends on the electron density and the fundamental quantum of flux. When the magnetic field is decreased, the number of available quantum states per Landau level reduces. This forces electrons to redistribute among the remaining levels, leading to a transition from one quantized state to another. This redistribution explains why the resistivity suddenly jumps as the field is tuned. The system transitions from one integer quantum state to the next, leading to an observable shift in the resistivity. Conclusion. The discovery of the quantum Hall effect was more than just a breakthrough in condensed matter physics. It redefined the way we measure electrical resistance. Today, the von Klitzing constant serves as the universal standard for resistance, allowing for measurements with unprecedented precision. Beyond metrology, this phenomenon paved the way for new fields of research, including topological quantum physics and the study of fractional quantum Hall states, where interactions between electrons lead to even more exotic quantum behaviors. The integer quantum Hall effect remains a cornerstone of modern physics, providing a clear demonstration of how quantum mechanics governs macroscopic electrical properties. Its precision, robustness, and fundamental significance continue to inspire new discoveries in condensed matter physics and beyond. If you found this exploration fascinating, don't forget to like, subscribe, and share. Stay tuned for more deep dives into the quantum world here on Quantum.